Hi, my name is Juan Chicatoro, and today I'm going to be presenting trick or hit manipulating temperature-based control systems using rectification attacks by Yaju and others. This work was published at ACM, CCS, which is one of the top-tier conferences in computer and system security. The paper focuses on a fundamental assumption in cyber-physical systems that sensor measurements accurately reflect the physical world. What I'll show today is that this assumption can be fundamentally broken. Specifically, the authors demonstrate that an attacker can manipulate sensor readings purely through physical interference, without modifying software, hardware, or network communication. This is important because it challenges a core principle in secure system design, that if computation and communication are protected, then the system is safe. In reality, this work shows that the control loop itself can be deceived at the physical layer. The core idea of this paper is simple but very powerful. Modern cyber-physical systems operate using a closed-loop control. They continuously sense the environment, make decisions, and act based on control sensor inputs. This means that the sensors are implicitly trusted as ground truth. However, this paper shows that this trust can be violated. Specifically, an attacker can manipulate sensor readings externally without compromising the system itself. As a result, the system's perception of reality is no longer accurate. It is attacker control. This breaks a fundamental assumption in control systems that sensor measurements reflect the true physical state. And once that assumption is broken, the control loop does not fail and continues to operate correctly but on incorrect data, which means the system behaves as designed but produces unsafe outcomes. This is particularly dangerous because traditional security focuses on protecting computation and communication, but not the integrity of physical measurements. This becomes especially important when we consider where these temperature sensing systems are deployed, that are used in safety-critical environments such as infant incubators, vaccine storage systems, and industrial control systems. In these settings, maintaining the correct temperature is not optional. It is essential for safety and correct operation. These systems operate in closed-loop control, meaning they continuously read inputs and adjust their behavior in real time. As a result, the system does not just observe the environment, it actively responds to it. So if an attacker manipulates the sensor input, the system will amplify the error through its control actions. This means that a small manipulation in the sensor can lead to large unsafe physical outcomes. This is not just a data integrity problem, it is a direct threat to the physical safety. And as the paper demonstrates, these effects can be induced on real systems, meaning the risk is practical, not just theoretical. In control systems, bad data doesn't stay bad. It actually gets acted on. The root problem addressed in this paper is the implicit trust placed on sensor data. In most control systems, sensors are assumed to be inherently trustworthy, and their outputs are treated as ground truth. However, there is typically no integrity validation at the physical layer and no mechanism to authenticate the origin of the measurements. Security mechanisms are usually applied at higher layers, such as networks or software, but not at the point where data is generated. This creates a critical gap in the system trust boundary. As a result, any signal that reaches the sensor interface is accepted as legitimate input to the control system. This means that the system cannot distinguish between a genuine physical measurement and an adversarially injected signal. And because the control logic relies entirely on these inputs, these blind spots enable direct manipulation of system behavior. In other words, the system secures communication, but not perception. This paper makes several key contributions. First, it demonstrates a novel physical layer attack on temperature sensing systems. Second, it identifies and characterizes a previously underexplored vulnerability, the rectification effect in analog amplifiers. Third, it shows that electromagnetic interference can be used to induce a controllable DC offset in sensor outputs, effectively spoofing measurements. Fourth, the authors validate these attacks on real-world systems, including safety-critical devices such as infant incubators. Finally, they propose a low-cost anomaly detection mechanism to mitigate this class of attacks. Importantly, this work is not purely theoretical. It combines analytical modeling with experimental validation on real hardware. This is particularly impactful because it bridges circuit-level behavior with system-level security consequences. The core insight of this paper is that attackers can spoof sensor measurements without compromising software or system logic. Instead, the attack exploits analog circuit behavior, specifically the rectification effect in amplifiers. By injecting electromagnetic interference, the attacker introduces a high-frequency AC signal that is converted into a DC offset within the sensor circuitry. This offset directly alters the sensor output, effectively changing the measured temperature. Importantly, this occurs before digitization, meaning the analog-to-signal converter receives already corrupted data. From the system's perspective, the data is completely valid. As a result, the control system operates normally, but based on false inputs. This allows the attacker to bypass software layer defense entirely and by manipulating the signal before it ever becomes digital data. To understand the attack, we need to look at how sensor signals are processed in a typical system. The sensor produces a low-amplitude analog signal, which is then passed through a signal conditioning circuitry and amplified. This amplified signal is digitized by the ADC and then used by the control system to make decisions. The critical point in this pipeline is the amplifier stage. Because the signal is very small, amplification is necessary, but this stage also introduces a vulnerability. Specifically, due to nonlinear behavior in the amplifier, injected electromagnetic signals can be rectified, converting a high-frequency AC signal into a DC offset. This offset directly alters the signal before it reaches the ADC. As a result, the system never observes the true sensor value, only the manipulated one. And because this occurs before digitization, the system has no mechanism to verify the integrity of the signal. So this is going to be where the signal is originated. The dotted one is going to be the vulnerable region. This is where the signal is injected and then becomes like a DC offset. And then at this point, the data is already corrupted. So the vulnerability isn't in the sensor itself, it's in how the signal is processed. This attack works because amplifiers exhibit nonlinear behavior. When a high-frequency electromagnetic signal is injected, it alters the amplifier's operating point or bias. Due to this nonlinearity, part of the signal is rectified, producing a DC voltage offset at the output. On the left, we see how the effect depends strongly on frequency. Only specific frequencies produce significant temperature shifts. On the right, we see that increasing the signal power allows the attacker to scale the effect in a controlled way. Importantly, this offset is not random. It is stable and predictable. This means that the attacker can control both the magnitude and direction of the offset by adjusting the frequency and amplitude of the injected signal. Since voltage maps directly to temperature, this produces a controlled change in the sensor reading. So this is not noise or interference in the traditional sense. It is deterministic and controllable signal manipulation. We assume an adversary with the following capabilities. First, the attacker does not require any direct access to the target system. There is no need for hardware or software modification. The attack is performed entirely externally using electromagnetic signal injection. Additionally, the attacker can operate from a distance of several meters, and the signals can penetrate common physical barriers such as walls. Importantly, this is a black box attack. The adversary does not need internal knowledge of the system's design. These assumptions are consistent with experimental setup in the paper, demonstrating that the attack is both practical and realistic. As a result, this significantly expands the attack surface and increases the risk of exploitation in real-world systems. This slide summarizes the attack process step by step. The attacker begins by injecting an electromagnetic signal into the system. The signal targets the amplifier stage, where it is rectified into a DC offset. That offset alters the sensor measurements before it is digitized. As a result, the control system receives incorrect data and executes incorrect control action. What's important here is that the attacker can precisely control the output, increasing or decreasing the signal in a stable and repeatable way. So this is not a one-time disturbance, it is a continuous and controllable manipulation. And because the system relies on feedback, it actually amplifies the impact of the attack through its control loop. To validate the attack, the authors design a controlled experimental setup. They inject electromagnetic signals into the sensing circuitry and measure the resulting voltage at the amplifier output. A key part of the methodology is a frequency sweep, ranging from 10 MHz to 1.5 GHz. This is important because the effectiveness of the attack depends strongly on frequency. Certain frequencies interact with the circuit more effectively and produce larger DC offsets. As shown in the image, a signal generator injects the EMI into the circuit and targets different points like P1, P2, P3, P4, and P5 in the signal path, while the output is monitored using an oscilloscope. The goal is to identify frequencies that maximize the induced DC offset, allowing the attacker to optimize the manipulation. In addition, the authors validate the attack on real-world sensor systems, demonstrating that the effect is not limited to a controlled lab setup. This shows that the attack can be systematically tuned and reliably produced. So again, this is going to be the EMI source. We have injection points. We have the amplifier where the rectification occurs, and then the oscilloscope where the output is measured. So bottom line, the attacker is effectively tuning the circuit like an antenna to maximize the attack effect. Key result is that increasing EMI power produces a larger induced offset. There is a clear and approximately monotonic relationship between signal power and the magnitude of the offset. This gives the attacker a second control dimension, not just frequency selection, but also amplitude tuning. In the top plot, you can see how specific frequencies produce positive or negative offsets, while in the bottom plot, the AC component remains relatively small at those points. By adjusting the transmit power, the attacker can scale the offset up or down in a controlled way. This enables fine-grained manipulation of the sensor reading. So again, this is not random noise, it is deterministic control. In effect, the attacker gains a continuous control variable over the system output. So top plot, different frequencies produce different DC offsets, both positive and negative. And then bottom plot, the AC component stays low at those optimal points, meaning the signal looks clean. So at this point, the attacker isn't just injecting interference, they're tuning the system like a control input. The attack can also be performed wirelessly without any direct connection to the system. However, it requires precise frequency tuning since only certain frequencies effectively couple with the circuit and produce significant offsets. As shown in the plots, the magnitude of the induced DC offset varies with both power and frequency and decreases as distance increases. Despite this, the attack remains effective over several meters and can even penetrate physical barriers such as walls. This is important because it shows the attack is not confined to a controlled lab conditions. It is practical and deployable in real-world environments, significantly expanding the attack surfaces. So in the left plot, we can see increasing power increases offset, and in the right side plot, different frequencies are going to produce different effects. This turns what we typically think of as a local attack into a remote one. The manipulated signals produced by this attack are stable and consistent over time. They are not detected as noise because they appear as valid sensor measurements within the expected operating range. As shown in the graphs, the attacker can introduce control step changes in the output, which remain stable until the input is adjusted again. This demonstrates precise control over the sensor output. Critically, the system cannot distinguish between genuine and manipulated data, since the signal follows the same characteristics as legitimate sensor behavior. As a result, the attack is both stealthy and reliable, making it particularly difficult to detect in practice. So we're going to have the baseline, which is the normal operations. Then the attacker increases output in control-like steps, but they can also decrease it. And then it returns to normal once the attack stops. From the system perspective, nothing is wrong, and the data looks completely normal. Authors validate the attack on real-world sensors, demonstrating that vulnerability is not limited to theoretical models or lab-only setups. They show that multiple types of temperature sensors are affected, indicating that this is a general issue across different hardware designs. These results also show that the attacker can both increase and decrease the reported temperature by adjusting the attack parameters. In the plot in the left, we see how the magnitude of the temperature shift changes with the distance, decreasing as the attacker moves farther away. On the right, we see that the increase in the signal power allows the attacker to scale the effect in a controlled way. For example, a temperature reading can be shifted from approximately 29 degrees Celsius to 35.5, a clinically dangerous range in applications such as infant incubators. This demonstrates that the attack is not limited to small perturbations. It can induce large, significant safety-critical deviations. In other words, the attacker can directly influence physical system behavior through manipulated sensor data. So what do these experiments ultimately demonstrate? Collectively, they show that the attack is precisely controllable, can be performed remotely, and is effective on real-world systems. They also demonstrate that it bypasses traditional software layer defense, since manipulation occurs before digitization. As shown in the plots, the attacker can introduce stable, stepwise changes in the measured temperature over time. Importantly, the paper goes even further. The authors demonstrate that they can encode patterns to the sensor output, effectively writing signals such as simple shapes or characters. So here they just wrote like the word hi. This highlights the level of control that the attacker has over the system. This is what distinguishes the attack from typical electromagnetic interference. It is not random noise, it is deterministic, repeatable, and programmable manipulation. Ultimately, this validates the core claim of the paper. The assumption of trusted sensor measurements is a fundamental vulnerability in cyber-physical systems. Vulnerability affects a wide range of real-world systems. These include medical devices, laboratory equipment, industrial control systems, and IoT controllers. The results shows that multiple types of temperature sensors are affected, including thermistors, thermocouples, and RTDs. More importantly, the magnitude of the effect is significant. In some cases, temperature readings can be shifted by tens of degrees Celsius. The experiments also show that these attacks can be performed from distances of several meters, depending on the system. The key takeaway is that vulnerability is not tied to a specific device. It stems from a common design pattern, analog signal conditioning followed by digitization. This means that the attack applies broadly across many domains, making it a systematic issue rather than a niche vulnerability. So we have this table that just portrays that different devices all are affected, different sensor types, all for vulnerable. Magnitude, we have large deviations, and then in distance, remote, how feasible it is to perform remotely. So bottom line here is this is not a device-specific flaw, this is a design-level vulnerability. This is the most impactful demonstration in the paper. The author performs the attack on a real infant incubator, a safety-critical medical device. They are able to increase the reported temperature by approximately 8.5 degrees Celsius or decrease it by about 4.3 degrees. These changes are achieved within minutes and from a distance of about 1 meter, and critically without triggering any alarm. This is extremely dangerous because infants rely on precise thermal regulation, and even small deviations can have serious consequences. From the system's perspective, everything appears normal. It is simply active on incorrect sensor data. This means a life-critical system can be manipulated from the outside without any indication that something is wrong. This is not a hypothetical vulnerability. It directly translates into real-world patients' risk. The reason no alarm is triggered is that the system implicitly trusts sensor measurements. When the sensor is spoofed, the system's entire perception of the environment is compromised. The control logic and alarm mechanisms are functioning incorrectly, but they are operating on incorrect data. As a result, the system observes normal conditions and continues to behave as expected. This highlights a fundamental limitation. The system has no way to verify whether its inputs reflect reality. In other words, the system is not failing, it is being deceived. Traditional defenses assume the data is incorrect, but here the data itself is the attack. Traditional defenses are ineffective against this type of attacks because they are not designed for adversarial physical layer signals. For example, filtering can be bypassed by carefully selecting attack frequencies that pass through a system's signal path. Similarly, shielding is not sufficient against targeted electromagnetic interference, especially when the attacker can tune both frequency and power. More importantly, software-based defenses cannot detect this attack because the signal appears as valid sensor data. This highlights a mismatch in the security model. The system assumes trusted inputs, but that assumption is violated at the physical layer. To address this, the authors propose a signal-level anomaly detection. The idea is to monitor frequency domain characteristic of the signal and identify abnormal high-frequency components introduced by the attack. If such anomalies are detected, the sensor reading can be flagged as unreliable. While this approach does not prevent the attack, it provides a practical way to detect it by shifting the focus from prevention to detection. So this would be a traditional pipeline, but then we're adding this anomaly detector. So the purpose of the anomaly detector is just to detect frequency spikes. So we're trying to secure the system, but we're not securing the signal. While the attack is powerful, it does have several limitations. First, it requires precise frequency tuning, since only specific frequencies produce significant effects in the target circuit. Second, the effectiveness depends on the hardware design. Different circuits respond differently to electromagnetic injection. The attack is also limited by distance, as signal strength decreases with range. In addition, the attacker may need to identify or search the system's resonant frequencies to maximize the effect. However, these limitations do not eliminate the threat. They primarily affect the ease of execution, not the feasibility of the attack. These constraints make the attack harder, but not impossible. To conclude, this work shows that sensor measurements cannot be assumed to be inherently trustworthy in cyber-physical systems. It demonstrates that attackers can manipulate sensor readings remotely without modifying software or hardware. This exposes a fundamental gap in security models, which focus on digital threats while assuming the physical layer is reliable. As a result, securing this system require extending trust and verification beyond software into a physical layer itself. Bottom line, security doesn't fail because the system is broken. It fails because the system is trusting the wrong thing. Ultimately, this paper forces us to rethink a fundamental assumption that sensors represent reality. Because if a system blindly trusts its sensors, you're effectively giving control of the system to whoever controls the signal.